Did everybody make it up through, we kind of jumped around a little bit, question 19.6? Okay, I think that's where the last person left off. Okay, so we sort of jumped around a little bit on Friday. That's because for a couple of these things, we say we'll explain it later, then we go and explain it, and then we've already forgotten what we've done, so we're not sure where to apply it. So we sort of jump around during that discussion section. All of you guys were exposed to complex equilibria as well on Friday, yes? Okay, and it made complete sense the first time you did it, and you're ready for the exam? Yes, good. All right. So, we'll have some time to go over those today. We'll start right around question 19.7. And then we'll pretty much go straight through, skipping over the stuff that you guys have already talked about, but getting more practice on the things that we might need. So, for starters, what we'll do, we talked about saturated calcium carbonate solution having a basic pH about 10. Now, best question to ask when everybody says to you, a fact, tell them to prove it. Now we can do that pretty simply in the lab. We got a bunch of calcium carbonate here. Pretty large spatula. It was actually the smallest one that was in there. Totally crazy. So, I'll take some calcium carbonate and throw it in my DI water. And it doesn't take much. Would take much less than this to make a saturated solution. So you see it's kind of frothy. Not all of it goes in, but some of it does. We know that from the chemistry that we studied thus far. So, have you guys been exposed to phenolphthalein indicator? Maybe in the lab, Gen Chem 1 or 2? All right. So, what would we expect to happen as I add phenolphthalein indicator to a saturated solution of calcium carbonate, given what you've been told? For those of you that might not remember, in a basic solution, phenolphthalein turns pink. So, we can use indicators to tell us roughly about what pHs are. Tomorrow, if I can get it to work, I'll have a demo set up with a pH meter, and we'll talk about a couple other interesting saturated solutions of calcium carbonate, and we'll talk about their exact pHs. So, proving to ourselves that yes, calcium carbonate forms a basic solution because of that basic anion carbonate. That's what also makes the problems a lot more fun to solve, because we have to take into account more than one equilibrium most of the time. So, is everybody okay with the material that led up to question 19.6? So that was basically, we're given the pH information, pH equals 10 for saturated calcium carbonate, and we go through and we solve for S. Does anyone have any questions on that? Because all the material that we're going to do today, maybe tomorrow, is going to be building on that stuff. So if you have a question, I would suggest you go ahead and ask it now. If you feel a little bit lost, just let me know and we can just go ahead, start from a little bit further back. Yep. No, okay. All right, so we'll start question 19.7. So, if at 25 degrees C, saturated aqueous solution of a semi-soluble carbonate salt, I just called it MCO3, could be anything, shows a pH of 11.0. Well, what does that tell us qualitatively about the solubility, or about its solubility compared to calcium carbonates? Well, we know the pH is greater. pH 11 here, pH 10 for saturated calcium carbonate. So, this suggests that the S, molar solubility, has to be greater or less than 1.4 times 10 to the minus 4, that for which we just solved above. What do you think? You got a 50-50 chance, right? Greater than, exactly. Now, the question is why, of course. That's the most important question always. He even says it right there. Now, this is because in order to increase the pH, I have to increase the concentration of the base in solution. The only base in solution is going to be carbonate. So you have to put more carbonate into solution, more base, greater pH, greater S. So all that kind of comes together. All right. Horvath's word of caution. On recognizing that the Bronsted-Lowry basicity of carbonate ion must be considered regarding calculation of S for the semisoluble salt, it is tempting to write this EQ that I've written up here. It's also right down in your textbook. But this isn't okay to write, because what that equilibrium is telling us is that every mole of carbonate ion that I form is turned into a mole of bicarb ion. We know that's not true. We know that CO3 carbonate ion is a weak base, and if it's just put in a solution of water, it's not going to ionize at 100%. Now, we can change that chemically. We'll see that a little bit later on. But this EQ is not appropriate to write for just a saturated solution of calcium carbonate in water. The reason being, again, carbonate ion has a Kb, and it's not very large. So, we need to make sure that we're able to quantify that HCO3 because it's not stoichiometric. I think that's the word that he uses in the text. This doesn't go 1 to 1. So, that's not the EQ that we write, though it's tempting to write. In this situation, we actually can't write that, and we have to go through and solve for S a different way. So, any questions on that stuff? Question 19.7 on writing equilibria? Okay. So, what we're going to move on to now. Calculation of S from KSP and KB. Now, as it turns out, we don't actually need pH data. We don't actually need to go into the lab and figure out the pH of the solution to fill in one of our data points. Because, as it turns out, there's chemistry happening here that we didn't necessarily take into account on pages 19.5 and 19.6 when we were given that pH information. So, chemistry that happens when I take some of that calcium carbonate and put it into water. First, solid calcium carbonate dissolves into calcium ion and carbonate ion. We know this. KSP stuff, pretty simple. Additionally, the carbonate ion acts as a base. Pulls a proton off of water, leaving you with bicarb hydroxide ion. Now I've went ahead and I've written down those two K values. KSP calcium carbonate, KB carbonate ion. These are going to be of importance to us. Now we know these. These are numbers you can pull off your information table. So if you see this on an exam, you see it on a bonus quiz, always want to pull out all the information that you possibly can before you go solving for other numbers. So, here's the chemistry, and there's the numerical information that we've got. Now, I know that my only appreciable source of hydroxide ion in this system is going to be from carbonate ion, right here. Which also tells me the only source of bicarb, carbonate ion. So if I look at this equilibrium here, I can tell myself that the concentrations of bicarb and hydroxide ion are very likely close to the same, if not numerically the same, to the two sig figs that we've been given here. So we'll call those X, bicarb and hydroxide. Now, carbonate ion. Initially, before the carbonate ion has any reacting to do, we dissolve calcium carbonate into calcium ion and carbonate ion. Now, my initial carbonate ion can just be called S. But I'm going to lose a fraction of that to Kb. So to account for that, S, and I subtract off the amount of bicarb that I make. So, does that make sense, our variable choice here, before we go ahead and do some algebra? Okay, so what we can do now is we can set up a system of equations using KSP and KB. They give us two equations, two variables. This one's pretty easy to solve. I spent a couple minutes with it, and I don't know if I wrote down what I got. I did a lot of pretty hasty cutting off of numbers. I didn't save any of my significant figures. I got, I think, 1.3 times 10 to the minus 4 for S. And that doesn't take too long at all here. And I didn't solve this rigorously. I just substituted one for the other and took educated guesses at S values. So, Dr. Horvath has in parentheses, in bold italics, for practice work through this. So go ahead and do that. Shouldn't take you very long at all. What I did is I went through and I left S as my only variable. And from there I just went ahead, did Dr. Horvath's educated guess and check method. Doesn't take long. So that's calculation of S from KSP and KB. So if you're not given a piece of information that you think you need, Dr. Horvath wouldn't stick it to you like that, though it feels like sometimes on a test that you're missing information that you need. If you think you're missing information, write down everything that you know, and also make sure that you understand what equivalencies you might be able to set up to simplify your math. And that'll get you to the right answer. So any questions on that before 19.8? All right. So, question 19.8. pH of silver sulfide, Ag2S, has a pH of 7.0. What does this tell us about its solubility? What was that?
It's neutral.
It's neutral. Well, okay, we know it's pH neutral. What does that tell us about its S value, though? Small. Now, why is that?
It's basically water.
If I have this reaction here, sulfide ion reacting with water to give us HS minus and hydroxide ion. If I just want to speculate on the extent of that reaction, what's that going to be?
100%.
100%. This is one of our two very, very strong bases. So, I know S2 minus, very, very strong base. Silver sulfide. That's going to produce for us a very strongly basic anion. But its pH is still 7.0. So I've got to be dumping practically 0 sulfide ion into solution, because this reaction is going to go 100%. So even a small concentration of sulfide is going to affect your pH, even out to this significant figure here. So it follows that the KSP of silver sulfide is what, 10 to the minus 51 or something like that? That's one of our smallest. I don't have it written down here. Should be on your information tables. But it does follow silver sulfide, very, very sparingly soluble. I think that might be the lowest number on your table. All right. Now, if there are no other questions regarding that stuff, we're going to move on to a slightly more interesting system, wherein we're going to calculate S for calcium carbonate buffered at pH 8.00. We remember that saturated calcium carbonate in water, what we got right here, is pH 10. So we're making the solution more acidic, pH 8. How many times more acidic? 100, yep. Want to remember your pH mathematics always. So, another important consideration that we want to make regarding the concentration of carbonate ion in this solution at equilibrium. Question 19.6 asked of you the percent ionization of carbonate ion at pH 10. And what was that?
So it's like 70%.
About 70%. So, if I'm going to make my solution 100 times more acidic, if I'm just dumping protons into this solution, dumping H plus into this solution, what do you think that percent ionization is going to look like. It's going to be pretty close to 100%. pH 10, we're already ionized 70%. 100 times more acidic, this is what I'm going to bet on. We're going to prove it to ourselves later, but this is the kind of thing that'll really help you solve a problem if I think, okay, well, for starters, I probably don't have much carbonate ion around because I'm acidifying my solution by quite a bit from one I've studied before. So, let's see here. That's the point that he makes in the second little paragraph there. Now, that equilibrium that we wrote before, that wasn't really good, in this case is going to likely hold for us because of this. So, take my calcium carbonate, add it to water. Since the solution is pretty acidic in comparison to plain old saturated calcium carbonate, my guess is that I'm going to get a lot of bicarb ion, primarily that. All aqueous ions. So this is the equilibrium that I'm going to write for this reaction. Dr. Horvath has it written down there for you. Now, here's where we go back to those complex Ks. This one's a pretty easy one to solve. You guys were exposed to something a little bit more complicated the other day. But this K is going to be concentration bicarb, concentration hydroxide ion, concentration calcium 2+. A very common mistake that we see on exams and quizzes. People put in pure solids, pure liquids into K expressions. They don't belong there. Even in a complex K, all the rules still apply. So, you want to make sure when you're writing something like this, include your phase labels, because a lot of the time it's easy to forget. It's, calcium carbonate is really a reactant here? Well, not really. It's a pure solid. It's just an equilibrium with its aqueous ions, in which we are interested. So there's K. Now, obviously, in our information sheets, we don't have the number for that K written down. But using just that information, I can go through, take this K, and multiply it through by factors of 1 until things like KSP, KW, KA, KB fall out. We'll deal with another K, KF. That's a little bit later, though. So, the first thing that I'm going to look at, I see, well, I have calcium carbonate right there, and it dissolves. So I want the KSP for calcium carbonate. So I'll multiply this. I have calcium here, so I'm going to multiply this by a factor of carbonate ion divided by concentration carbonate ion. Now, you'll note we haven't changed anything. Again, this is just multiplying by 1. That's the beauty of this little procedure. So, I can check these two off. Calcium and carbonate ion. And just call that KSP, calcium carbonate. Now, I'm going to take a look at what's left over. I'm going to work on that. I can forget about this, KSP, calcium carbonate. It's gone. I can now ignore these two terms. What I'm going to do now is see, well, okay, well, I've got carbonate ion, denominator, hydroxide ion, bicarb ion, numerator. Well, that's a really easy one. That's just Kb carbonate ion. So this is KSP calcium carbonate. KSP CaCO3 times Kb carbonate ion. And that's all there is to it. Now what you guys are going to see in the future are things where you have to multiply through by 3, 4, 5 different things. But that's really the gist of the procedure. If you can do it once, you can do it more than once. It just turns into a fun little logic problem when you're figuring out what you're going to need to pull out from the initial equilibrium that you've written down. So that's sort of our first taste of the complex equilibrium today. Dr. Horvath says in the book that we'll go over it later. You guys have already seen some of it, so that's good. Now this is our complex K. You can get the number. All you have to do is multiply KSP calcium carbonate by KB carbonate. Now, Dr. Horvath probably gives us the number here. 1.3 times 10 to the minus 12. Okay. Now, let's take a step back here. I've got my K value. Now I'm going to have to do some math here soon to find some unknowns. But before we do that, we're going to want to write down what all 3 of our unknowns are going to be. So, we'll start with the easiest one. Concentration hydroxide ion. What is it?
1 times 10 to the minus 6.
That's just a number. Always remember, if you're given pH, you're given both concentration of hydronium and hydroxide ion. That's something that people forget a lot, but that's a little hint that'll point you in the right direction. Now, second easiest one. We don't know its concentration explicitly yet, but what am I going to call the concentration of calcium ion?
S.
S. Bless you. Because I know the calcium ion isn't going to engage in any chemistry once it becomes calcium ion. That's going to be our rock, just S. Now, what do we think about bicarb ion? This is a tougher one. So, I know that S is going to be equal to the sum of the concentrations of all of my carbonate-containing species. Now, this would make the math a little bit more difficult, because here I've got 3 unknowns, all in equilibrium with each other, presumably. Because again, bicarb has a Ka, Kb, some of that bicarb is going to go back to carbonate, some of that bicarb is also going to turn into H2CO3. So, what we're going to do is we're going to prove to ourselves that at this pH, bicarb is the only thing that exists in appreciable concentration. How are we going to do that? We'll take advantage of the fact that we know Ka and Kb of bicarb. What's the Ka bicarb? Should be right there in the book.
Ka is 4.8 times 10 to the negative 1.
All right. So, I'm not looking for numbers here. What I can dig out of this thing is actually just a ratio between my concentration carbonate ion and my concentration of bicarb ion. So if I'm just trying to prove to myself that there's not enough carbonate ion around for me to care about, I can just go ahead, give it the big ugly axe here, simplify my math a little bit. It's nice to make things easy. Most of the time we can. So, what's the concentration of hydronium ion in this solution? 1.0 times 10 to the minus 8. So, divide through by that. And there's my ratio, carbonate to bicarb. As 4.8 times 10 to the minus 11 is 1.0 times 10 to the minus 8. Now, is that a big number or is that a small number? Pretty small. Turns out, if you go ahead and you rearrange it, your ratio of bicarb to carbonate, 210 to 1. This is significant. Significant enough for us to axe out carbonate ion in our S expression. Now, the next thing I'm to worry about, H2CO3. We'll apply a similar procedure, taking advantage of Kb, bicarb ion. Now, we can do the exact same thing here. Now, if you're doing this kind of thing again on an exam, on a bonus quiz, I haven't taken a look at the bonus quiz you have now or the next one that you're going to get. Wouldn't surprise me if you have to do something like this, maybe with the phosphoric acid, the stuff that's got 3 protons attached to it. You're going to have to go through this math quite a few times in the future. Now, here I'm considering Ka. I dealt with hydronium ion concentration. Here I'm dealing with Kb. Therefore, I have to be concerned with hydroxide ion concentration. That's a really easy mix-up. So hydroxide ion concentration, get it from right over there, 1.0 times 10 to the minus 6. Now we can get Kb from our acid-base table, not explicitly, but we can solve using Kw. And that Kb value is 2.4 times 10 to the minus 8. We arrange this once again to get our ratio, H2CO3 to bicarb. Same thing we did before. We have another small number, 10 to the minus 8 over 10 to the minus 6. Turns out to be 42 to 1, bicarb to H2CO3. Now, also significant. I would say pay attention to it if it's a ratio of, say, less than 10 to 1. 10 to 1, 9 to 1, 8 to 1. We'll look at one of these in the near future where we'll have to pay attention. 42 to 1 though, good enough for me, good enough for us. So, we can now say calcium ion is equal to S. That's approximately equal to my bicarb ion. A couple of little deviations here, but nothing that's going to creep into the number of significant figures that we are using. So, all we have to do is go back to our original K. S squared. From here, S and S. And my hydroxide ion concentration. And we know what that K is equal to, because we solved for it earlier. 1.3 times 10 to the minus 12. And you can go ahead through, divide that, root it, and that'll give you S equal to 1.1 times 10 to the minus 3 molar. So, what we did here, to recap this entire problem, we started by making an assumption. pH 10, carbonate ion hydrolyzed 70%. pH 8, 100 times more acidic, probably pretty close to 100. We'll have to check back on that later. Take a look at the chemistry of the system. This EQ is probably going to hold. We could have proved that to ourselves beforehand by doing this. We sort of went a little bit backwards. So, we write an EQ expression. That EQ expression gives us a complex equilibrium by which we multiply carbonate ion over carbonate ion to give us two separate K values that we know. We multiply these two together to give us the value of our complex K. After that, we go ahead through. We look at the things we don't know, and we try to name them. Hydroxide ion, we can give that a number. Get rid of it. Easy. Calcium ion, again, easy. That's just S. Now to prove to ourselves that bicarb ion is also approximately equal to S, we go through Ka and Kb to get the ratio of bicarb to carbonate and bicarb to H2CO3. From there, we're able to tell ourselves carbonate, H2CO3, for all intents and purposes, do not exist in this solution. But we can go ahead through, simplify HCO3 bicarb to be S, and make the math really easy on ourselves. 1.1 times 10 to the minus 3 is a good number. So any questions on what we did here? Okay. So, now what I think you guys did yesterday in discussion, you guys jumped right into question 1910. Just started talking about it right away. Okay. This is K for complex equilibria. We're going to start going through those. Now, did anybody start at the top of section 19.3 to do calcium carbonate, H2CO3, that equilibrium? No, okay, good. This will be great practice for us. All right. So, you guys learned on Friday and yesterday, and earlier today, that in order to solve a complex K, we have to add some factors of 1 strategically to give us things that we know. So what we'll do is we'll take an example problem, which I think is just H2CO3 calcium carbonate. Okay. So, good. All right, you'll also see Horvath uses HOCO2. Try not to be confused by that. I think at some point, yeah, he switches over to CO3 2 minus, so, or HCO3. So those two are the same. It's like his sulfuric acid deal where he likes to write it HOSO, whatever. So he likes to write it just so that it tells you more about the structure, but I understand at this point you guys know the structure of the carbonate ion, so please don't let that trip you up. That's just what Horvath likes to write compared to what I like to write. So, this is our equilibrium. We take calcium carbonate, add some H2CO3 to it, going to give us calcium ion, and then we know carbonate ion, H2CO3 react to large extent with one another to give us 2 moles of the in-between bicarbonate ion. So, what we're going to do, we're going to write that K. Horvath calls it K star. Let's stick to that. So, K star. I see calcium ion. I see bicarb ion. I also see H2CO3. What am I missing from that K expression?
Calcium carbon.
What's that?
Or squared H.
Another thing that's easy to miss. We've been dealing with a lot of things, acids and bases in particular. Not used to looking at that stoichiometry. You always want to make sure to include that in a K expression. If you don't, you're going to have a very difficult time getting the correct answer for any of these questions. So, question. Top of page 19.9. How do we do it? Basically the process I described to you guys earlier. Dr. Horvath talks about Hess's law a little bit. This all does follow from the fundamentals of thermodynamics, which we'll begin to talk about maybe later this week. So you don't have to worry about that for now, but we know that K values are multiplicative, long story short. So if I can take this K star and I can turn it into an amalgamation, conglomeration, whatever the right word is, of K's that I know, KSPs, KAs, KBs in particular for now, what I can do is I can multiply those values together, and that'll give me the net K. K's are multiplicatives, the long story short that he's giving you guys on the first paragraph there. So, first thing that we're going to do, realize what's in solution here. Well, the first thing that I see, calcium carbonate. I want KSP calcium carbonate, because that thing's got to dissolve. So I'll multiply through by a factor carbonate ion over carbonate ion. Now, where does that leave me? What I'll do, before I start writing things down in other places, in case I make a mistake, I like to put little marks next to what I'm done with. So I know that in this thing, I'm going to have a KSP, calcium carbonate, in the numerator. Now, here I see H2CO3 acting as an acid. So I want KaH2CO3. So I'll multiply through by a factor of hydronium ion over hydronium ion. Now, what's that going to give me here? All right, KaH2CO3. H2CO3. Denominator, need that. Hydronium ion, numerator, need that. And then one of my equivalents of carbonate ion. So I'll erase this and I'll put a little check mark next to it. Now, I made check marks next to everything. To really make this clear to yourself, maybe you can use check marks for the first one, X's for the second one, smiley faces for the third one, hearts for the fourth one, whatever. But it's good to keep track of this stuff as you go through, because you don't want to be left with a stray hydronium ion, a stray hydroxide ion, because if that's alone, then you haven't solved the problem correctly, and you have to go through and make sure that everything's still there. Now, what else do I have here?
You have the bicarbonate ion, the carbonate ion left over, and the hydroxide. Well, that's
So, I got bicarb numerator, carbonate denominator, hydronium ion denominator. What can I do with that? Don't cheat and look at the textbook.
K for bicarbonate ion.
Ka bicarbonate ion. Now, is that just Ka bicarbonate ion? Inverse Ka. It's important to keep that stuff in mind too. It's important to know this stuff literally backwards and forwards. So, So, KSP, calcium carbonate, got that. Times Ka, H2CO3, I had one of those. Divided by Ka, bicarb ion. So, the most difficult step here is the very last one that we did, realizing that you see bicarb ion numerator, after it hydrolyzes as an acid, you're left with carbonate ion and hydronium ion. Now that is inverse Ka, or just 1 over Ka. So you can just throw it in the denominator. You don't have to think much more about it afterwards, except for looking at the number and then applying it correctly. So, Dr. Horvath has all the numbers written down for you there. The number associated with this K is 5.4 times 10 to the minus 5. So, now we'll know how to work on a system like this. If we need to look at one in the future, we'll probably revisit question 1910 in just a moment's time. But first, 19.9. Now, 19.9 asks us an interesting question. What if I don't want Ka in my denominator? What if I want to write this a little bit differently? I can, but I've got to know how. Now, what Dr. Horvath asks of us is, can this K be expressed as KSP calcium carbonate times Ka H2CO3 times Kb carbonate ion divided by Kw? Got that right, okay. So can we express that as Dr. Horvath has it written down in the textbook? And the answer is, of course we can. So K star, what I'll do is I'll just leave KSP calcium carbonate and KH2CO3. We're not going to touch those. And I'll split up KaHCO3 back into hydronium, carbonate, and HCO3 minus. Just kidding. So nothing fancy here, I'm just re-expanding Ka. Bear in mind this is inverse Ka, I almost made that mistake myself. Now, what am I going to do if I want Kb? I'm missing a factor here. I just wrote it down. Okay, no need to ask that question anymore. Hydroxide ion. So if I go ahead and I multiply through by hydroxide ion, what I see, carbonate ion, HCO3 minus, hydroxide ion, denominator, numerator, numerator, respectively. So I can rewrite this, KSP, calcium carbonate, Ka, H2CO3, numerator, Kb, carbonate ion, denominator, what I've got left over, hydronium ion, multiplied by hydroxide ion, Kw. Now, this all stems from the fact, as you all know well, Kw equals Ka times Kb of the conjugate base. That's another easy one to mess up. especially for something like carbonate ion. You want to make sure you're using the conjugate base's Kb value, not the Kb value for bicarb, because bicarb has both a Ka and a Kb value. It's tempting to use both to solve for Kw, but you'll never get the 1.0 times 10 to the minus 14. So remember, Kb conjugate base times Ka. Or whatever, Kb times Ka conjugate acid, whichever floats your boat. So that just stems from this right here. So if I wanted to figure that out, I have a Ka there, so I'll just express that as Kb over Kw. Algebraic rearrangement. So, any questions there? Just manipulating a complex K. They're not too hard to work with, so long as you know for what you're looking. Okay. So, question 1910. You guys got this on Friday, I think, right? We jumped right to there? Okay. So, do you want to go over this again? Did I hear yes? Yes, okay. So, we'll go over it again. Now, this one's a little bit more complex. So, this is the 1 plus 1. Question 1910 is calculate the mass of the sun. So, what we're going to do is we'll go ahead and write down this entire equilibrium here. So, silver chloride, water, H2S. Got it. All right, so this is the problem given to us. Balance it. And we are instructed to evaluate this K. We want a number. Make sure we know all of our phases. Remember, silver sulfide, silver chloride, both solids. Not important to writing our equilibrium expressions. So, we're going to go ahead and write K. Start with the numerator. 2 moles of product hydronium ion, 2 moles product chloride ion. Look in our denominator. Left-hand side, 1 equivalent, H2S. All right. So right there, that's our K. Now, what we're going to do is we're going to make it look a lot more complicated in order to make it simple. So, the first thing that we're going to start with, I see here silver chloride, but I've got 2 of them. And I also see, I can cheat a little bit, I've got chloride ion squared here. This is a big hint. This is going to tell us I am going to consider the solubility of silver chloride. Not only that, the only way I can get rid of chloride ions in this case is with silver ions. So instead of just doing concentration silver ion over concentration silver ion squared over the same. So what that's going to do for me, KSP, silver chloride squared. So, chloride, silver, good. Now we'll write down what we're getting for this K. Equals Okay. So, what else do I think I'm going to need here? See a couple of things happening. It looks like H2S is acting as an acid here. So I might need some hydronium ion. Okay, well I've got some of that. Maybe I need HS minus. That's a good place to go. So what can I pull out of this now?
The Ka of H2S.
Ka of H2S. Absolutely. So, Ka of H2S. H2S, denominator. Hydronium ion, numerator. HS minus, numerator. All right. We've got that. Now, let's continue to take stock here. What else do I think I need?
We're going to have to work in the KSP of AG2S.
AG2S, okay. So what's the KSP for AG2S? Not the number. What's that going to look like if that dissolves in water? I'll give you the easy part. That and what? HS minus and what else? Hydroxide ion. Now that was given to you here, but that's going to be expected to be something that you know. If you have something like silver oxide, silver sulfide, things like that, remember, it's not 2 silvers and 1 sulfide ion, because sulfide ion does not exist in aqueous solution. It dissociates immediately into HS minus and hydroxide ion. So, if I want that KSP, I'm going to have to go over here and use hydroxide ion. Now, does that make sense? Remember, special KSPs. So you're not dealing with any S2 minus ion. I don't ever want to see that written on a paper. So, looks like, since the only silver that I have left over is in the denominator, I'm going to have to go ahead and incorporate that into the denominator. So it looks like I've actually created for myself, using the 3 that I just checked there in the denominator, a KSP. Silver sulfide term. Now, with what am I left?
Hydronium and hydroxide.
Hydronium and hydroxide. So, hydronium ion times hydroxide ion, it's easy for us. KW. So, all that we've done is we took a reaction given to us, or we wrote down a reaction after Dr. Horvath tells you what you're mixing together. From that reaction, we derived a K. It is a complex K because I don't have on my information table, or any other information table for that matter, how that K is going to look numerically. So what I do is I multiply through by things I know I'm going to need. So here I see I have silver chloride. Silver ion is the first place to go. And then I saw H2S, definitely acting as an acid because I have sulfide ion. So I need KaH2S. And then, okay, I see over here, silver sulfide on the product side. But if I read this backwards, silver sulfide dissolves. KSP silver sulfide in the denominator. That's the way to think about that. That's the way I always do it. Think about, well, if I see it on the product side, the way it acts is fine as long as I put it in the denominator. Then I saw I have something left over, hydronium ion. But I have a hydroxide ion to simplify that into Kw. So that's really all there is to it. All you have to do is just really think about the question beforehand. What are you going to need? And you can just take yourself there by going through whatever method you choose. And you can go in a different order if you want to, but generally you don't want to try to pull out KWs and put in KWs. Those are sort of the leftovers, because if you start just multiply, you can keep doing that indefinitely and have as many factors of KW as you want in there. So generally KWs are left over, but you can do it in any order you want as long as it makes sense to you, and that enables you to get to the correct answer, which should be a huge frickin' number. What is it? Does he give you the answer here? 5 times 10 to the 9. That is huge. So not only does this reaction go, but you might not want to be in the same room while this reaction is going, because it's going to happen very quickly, and you're going to end up with a lot of silver sulfide. So again, that's what the big K value means. That means this thing, 5 times 10 to the 9, all the way over to the right. That's where that equilibrium is going to lie. And this actually stems from the fact that KSP silver sulfide, you see that in the denominator, that's our smallest one. He's got that written down, 6 times 10 to the minus 51. So it'd be very difficult for this not to be an extremely large number on the order of billions. All right, so that's question 1910. That's a really good example of a question that you might see quiz or an exam. So any more questions on what we did here? There's plenty of practice to be found for you guys on past exams, especially past summer exams where he's actually worked the problems. That's really advantageous. But always do them yourself first. Everything's easy once you know the answer. Okay. So if that's all right, and we have the time, we do. Move on to subset C, called the salt effect. So, we concern ourselves with this question. If I take a water solution, sodium nitrate, and I add some silver chloride to it, am I going to be able to dissolve more silver chloride in this solution than I am in a solution of silver chloride that only contains water, DI water? Now, the way we look at this, the answer is that S for silver chloride in the solution of sodium nitrate is actually going to be noticeably greater than S in plain water. Now this at first might not make logical sense. Well, I've got something else in the water already. Well, not if we write down the K expressions for these, because I know sodium nitrate dissolves completely in water. All sodium ions, nitrate ions. Now, I know that silver chloride partially dissolves into silver ion and chloride ion. That's an equilibrium with which sodium nitrate does not interfere. So something else is going on here. I have a silver plus ion here, an aqueous solution. Now, water's pretty good at dissolving ionic things. No doubt you've seen something like this before, where the little seagulls here represent HOH of water. So the negative dipole of water is going to direct itself towards a positively charged silver ion. Similarly, chloride ion is going to look different. Positive dipole of water is going to point towards the negatively charged chloride ion. This is why things dissolve in water, why ionic things especially dissolve quite well in water, except for some of these sparingly soluble salts, the reason for which we'll see later. Now, water, however, is neutral. We know this. Just H2O. So, if I take silver chloride and I dissolve it in water, okay, well, there's some drive to dissolve this because water wants to form these primary and secondary coordination spheres around this silver ion that stabilizes it and it orders the water. So that's good for the water. Now, if I take something charged, let's consider silver plus. What's going to happen is that water is going to get kicked out from immediately around this silver ion. And I'm going to have a cloud of nitrate ion. Surrounding my silver ion. So this is very similar to what water does in solution, only now I have charged particles. So rather than dipoles, I'm dealing with actual Coulombic charge. Similarly, all these chloride ions are going to be surrounded by many sodium ions. Now, we know that if I take silver chloride and try to dissolve it in water, that equilibrium lies more closely to solid silver chloride than it does its two ionic components. But if I go ahead and I have a bunch of nitrate ions, they're not bound to, but they're closely attracted to a silver plus ion. Similarly for chloride ion, I have a bunch of sodium ions. Again, sodium chloride we know is soluble, but chloride is going to find a lot of sodium ion, because I've got a lot of it, to surround itself. What I'm doing is I'm interfering with the ability of silver ions to find chloride ions, because what they have to do is they've got to push these nitrate and sodium ions out of the way. That requires energy. So, what I can say qualitatively for any semi-soluble salt is that S for that salt in a solution containing positive and negative ions that are not precipitators of the salt. I don't want sodium chloride because Cl is right here. We know what that does to solubility. Provided that this salt is not a precipitator of my solid, S will be increased in a solution as the one I have written up here. Always, always. This is called the salt effect. Now, we can't quantize this because that requires experimental measurement. So we don't have to do any math. But if you're looking at something and Dr. Horvath asks you generally, what do you think about S in a system like this if we added a certain salt? And then you'd be able to say, well, it's going to be greater. I can't say anything more, but my S value for silver chloride is going to be greater than what it normally is in DI water. And you can just figure that out from root KSP. So, is the salt effect okay? Basically, Coulombic attraction, preventing the two components of the salt from interacting with one another, pushing the equilibrium slightly further to the right. It's not going to dissolve at all, but it'll help. All right. So that's salt effect. Moving right along. D. Detection of an ion in solution by precipitation. Now we're given some KSP values here for a number of semi-soluble calcium salts. Given KSP, silver sulfate, calcium sulfate is what I said. Given KSP, calcium hydroxide. And you're given KSP, good old calcium carbonate. All right, so those values are 9.1 times 10 to the minus 6, 3.0 times 10 to the minus 5, and 6.2 times 10 to the minus 9, respectively. Now, the question that we're asking is if I have a solution of calcium ions, how can I detect for that by using the counter ions sulfate, hydroxide, carbonate? Well, what you would do is you would want to take a soluble salt of either or of any one of these three. Sodium sulfate's a good one here. Sodium hydroxide, even sodium carbonate. They're all fine. And what we'll do is we'll take a solution of sodium sulfate, say, and add it to water that we suspect has calcium in it. And if that water does have calcium ion, what's going to happen? Well, I've got sulfate ion in very high concentration, 0.1, 1 molar, something like that. Calcium ion in low concentration. Exactly how low we can figure out mathematically, but what's going to happen if I have appreciable calcium ion? CaSO4 is going to come out of solution. Similarly, I can precipitate out calcium hydroxide or calcium carbonate. Now, the question that we want to figure out is which one is best. So, what we're going to do is we'll take solutions of 0.1 molar sulfate, hydroxide, and carbonate, and we'll figure out for which one of these solutions is S the least. That is to say, which one of these is least soluble in the presence of a 0.1 molar concentration of each of these counter anions. So, the first one that we'll begin with, calcium sulfate. Now, the chemistry that occurs on dissolution is simply KSP. And I've got that number, 9.1 times 10 to the minus 6. Now what I'll do is, once again, Dr. Horvath has it written right here. We've taken a solution of 0.20 molar sodium sulfate and mixed it with a solution that might contain calcium 2+, so that the initial sulfate ion concentration is 0.10. So, I can replace SO4 2- with 0.1. And then I can go on through I can divide by 0.1 to find S for this solution. There we go. No more KSP. This is S. So we solved for the concentration of calcium ion, above which I will precipitate out calcium sulfate in a 0.1 molar solution sulfate ion. So what this tells us is that this procedure is extremely sensitive. I have calcium ion in such a low concentration, 9.1 times 10 to the minus 5. You'd never be able to tell. But then I add a little bit of sulfate ion, 0.1 molar solution, calcium sulfate crashes right out. And that'll be able to tell me about the presence of calcium ion. It's a very simple test. Testing by precipitation is a popular measure in analytical chemistry because of that high sensitivity for a pretty simple measurement. Now, do we have time for another one? No, we do not. Okay. So, that'll be all for today, guys. Take a look at the bottom of page 1911. Before tomorrow, we're going to go over the other two, and then we'll talk about how we compare them. And then hopefully we'll be able to move on to a couple more special topics in semi-soluble salts.